Have you ever looked at a complex chemical formula and just felt lost? Well, today we're going to crack a chemical code that's hiding all around us, in things like paints, medicines, you name it. We're diving into the world of coordination chemistry, which is really just the incredible architecture of complex molecules. Ready to solve the puzzle? Let's get into it.
Okay, so you see a formula like this one. Right off the bat, it looks kind of intimidating, doesn't it? You've got these mysterious square brackets, and it's not at all obvious what's actually connected to what. Think of this as our mystery for today, and I promise, by the time we're done here, you'll be able to look at this exact formula and know precisely what's going on inside.
So, to figure this out, we need to go back in time and meet a chemist named Alfred Werner. See, he was looking at these exact kinds of compounds and was just as stumped as everyone else. Why on earth did something like cobalt chloride suddenly behave so differently when you mixed it with ammonia? He was the one who finally saw the pattern, the hidden blueprint behind it all.
Werner's big breakthrough was this. He realized the central metal atom in these compounds is basically doing two jobs at once. Its first job, which he called the primary valence, is all about balancing its electrical charge. But its second job, the secondary valence, is all about construction. It decides exactly how many other molecules can physically attach to it, and that's what defines its 3D shape. And you can really see the difference between those two roles right here. That primary valence, it's taken care of by simple ions that just kind of float nearby, keeping the charge balanced. But the secondary valence, well, that's the architect. It's what forms the rigid directional bonds that create the molecule's actual structure, whether it ends up as a square, a pyramid, or something else entirely. And this classic example is where it all clicked for him. With his cobalt compound, he figured out that the 6 ammonia molecules were stuck directly to the cobalt, locked in tight. He called this the inner sphere. But the 3 chloride ions, they were just loosely hanging out in an outer sphere, ready to pop off in water. And just like that, this one simple idea of an inner and outer sphere explained everything. The puzzle started to make sense.
All right, so now that we've got Werner's blueprint, let's meet the individual building blocks. We're going to see how these complexes are put together piece by piece, almost like we're snapping together a high-tech model kit.
First up is the main frame of our model, what we call the coordination entity. This is everything you see inside those square brackets, the central metal atom and all the other bits and pieces directly attached to it. So whenever you see those brackets in a formula, you know you're looking at the solid core unit of the whole molecule. And what are those bits and pieces attached to the main frame? We call them ligands. These can be ions or just neutral molecules, and they're like the custom attachments that snap right onto that central metal. You can think of them as the tools, the arms, the sensors, whatever the complex needs to do its job.
So how many attachments can we have? Well, that brings us to the coordination number. In our original puzzle, K4FECN6, that number is 6. It's literally just a count of how many spots the ligands are attached to the central metal. This is the direct fulfillment of what Werner called the secondary valence. Simple as that.
Okay, so we know the parts now, but how do we talk about them? You can imagine chemists needed a universal set of assembly instructions, right? A system to name any possible combination of these parts. Now, it might look a little intimidating at first glance, but it's actually incredibly logical once you see the pattern.
Part of that system is just giving special names to our common attachments, our ligands. For example, a water molecule becomes aqua. And for any negatively charged ions, the rule is pretty easy. You just change the ending to O. So chloride becomes chlorido, and cyanide becomes cyanido.
All right, here are the assembly instructions. It's a pretty straightforward 4-step process. First, you always name the positively charged part, then the negative. Second, when you get to the complex in the brackets, you name the ligands in alphabetical order before you name the metal. Third, here's a little trick. If the whole complex part has a negative charge, you tack an 8 ending onto the metal's name. And finally, you finish it all off by stating the metal's charge using Roman numerals. Let's see how it works.
So let's finally solve our mystery. We apply those 4 rules to our puzzle molecule, and what do we get? Potassium hexacyanidoferrate 2. See how that works? Potassium is the positive part, named first. Hexacyanido tells us there are 6 cyanide ligands. Fer8 is because the whole complex in the brackets is negative, and the Roman 2 tells us the iron has a +2 charge. The code is cracked. But here's where it gets really cool. What happens if you have the exact same set of building blocks, the same metal, the same ligands, but you just snap them together differently? Well, it turns out a simple rearrangement can create a completely new molecule.
This whole phenomenon is called isomerism. And here's the crucial takeaway. This isn't just about looking a little different. Isomers have the exact same parts list, right? The same molecular formula, but because their 3D arrangement is different, their physical and chemical properties can be worlds apart.
Now, there are a few ways this can happen. With what we call structural isomers, the actual wiring between the atoms is different. It's like using the same electronic parts, but plugging them into completely different sockets. Maybe a ligand connects through a different atom, or two big chunks of the molecule just trade places.
And linkage isomerism is a perfect example of this. Take a look at this nitrate ligand, NO2. It can actually bond to the metal in two different ways, either through the nitrogen atom or through one of the oxygen atoms. If it connects via nitrogen, you get one compound. But if it flips around and connects via oxygen, you get a totally different compound with different properties. Same exact parts, just a different connection.
Okay, but let's push this idea a little further. What if all the atom-to-atom connections are exactly the same, but the molecule's overall shape in 3D space is different? What then?
Well, that leaves us to stereoisomers, like the geometric isomers you see here. In the cis isomer, the two similar ligands are on the same side of the molecule. Think of cis and sisters, side by side. In the trans isomer, they're on opposite sides. The bonds are all the same, but that different spatial arrangement can completely change how that molecule interacts with the world around it.
You know, the most mind-bending type of isomerism is something you can see for yourself right now. Seriously, hold up your hands. They're perfect mirror images of each other, right? But no matter how you turn them, you can never get them to line up perfectly. You can't put a left glove on your right hand. Some molecules are the exact same way. We call these non-superimposable mirror images enantiomers. And really, it all comes back to this one powerful idea. Isomerism isn't just some weird chemical quirk. It is, as the source material puts it, the reason compounds with the same formula can have wildly different properties. One version of a drug molecule could be a lifesaver, while its mirror image could be totally useless or even dangerous. Which really leaves us with a final massive thought. We've seen how a few simple rules build these incredibly complex structures, and how just a tiny twist in that structure can create something entirely new. So the real question is, if a tiny change in 3D shape can alter everything about a molecule, how does that one fundamental principle shape our entire world, from medicine to materials and even life itself? Now that's a code worth thinking about. Thanks for joining me.